Hello, my name is Ehsan Naeini. I am a senior research advisor with Icon Science. The title of my talk is Wavelet, Principles and New Advancements for Broadband Seismic Data. I've set this talk so that it's useful for you if you are a beginner or if you are a day-to-day practitioner. With that in mind, the outline of my talk is why Wavelet matters, how we do it, how we QC it, goodness of fit and accuracy, and finally, Wavelet for broadband seismic data, what is missing. So, Wavelet, why it matters and how we do it. As it stands, Wavelet is to correlate the well to the seismic, and from which we estimate a wavelet. That wavelet has interesting and important attributes such as lag, phase, and bandwidth. In this figure, the estimated wavelet has a lag. The same place for the top reservoir marker on the impedance obviously doesn't match that location on the seismic trace. If we want to pick the top reservoir attribute from the seismic, we have to consider the lag shown by green arrow. This is another example when the top reservoir marker on the log corresponds to the yellow horizon, and so the 3D map is shown on the right. With the lag in mind, the top reservoir on the seismic is the blue horizon, and you can see in the figure on the right that the sand anomalies are clearly separated from the shales and also conform to the geology. So the reason Wavelet matters, it's simply because you could avoid misinterpretation. It also matters because wavelets are what we use ultimately for inversion. Wavelets, when we estimate them, come with some uncertainty and errors. We have to keep in mind that those errors should be low so that the inversion results are accurate. In the figure below, if we have the ideal wavelets with zero phase error, we get the impedance profile shown in the middle. If the phase errors are starting to become higher, between plus and minus 10, the estimated impedance has a ramp. And also, if it's bigger, that ramp becomes more serious, and that could lead to under or overestimation of the porosity or other reservoir attributes later on. It's good to say it matters, but the next question is how we do it. Basically, the first approach is to model the earth filter. So let's say in marine, we can model the source signature through the sea, and then obviously from the sea bottom to the earth and come back. But that's a very difficult process. We are not just there yet. A more practical approach is to use convolutional model. Convolutional model is useful because the geologist sees the earth as a convolution of the reflectivity with the wavelet. So such approach is useful mathematically also because we can use least squares technique to estimate the wavelet. Perhaps the next big thing is to estimate the earth filter completely, but as I said, it's just too early for that now. With that in mind, Wavelet procedure can be summarized to 3 steps. Step 1 is edit and calibrate the sonic and density logs. Sonics usually by drift curve analysis, and density logs, if they suffer from washouts, we should correct for them. The next step is constructing a synthetic seismogram, and finally we match that synthetic to the seismic. Schematically, it's shown in the figure below. You can see that there is noise on the logs and there is also noise on the seismic side. And if we do a computation, we have to take into account both input and output noise. The filter, shown as EAGE, is often related to the cross-correlation or autocorrelation in the time domain or cross and auto spectra in the frequency domain. Such concepts bring forward the way we QC the Wavelet, that is goodness of fit and accuracy. Useful attributes to measure goodness of fit are cross-correlation, a typical attribute we often use, proportion of trace energy predicted by the synthetic, and also root mean square of the error or RMSE. Some useful attributes to measure the accuracy are NMSE, amplitude and phase error as a function of frequency, or a constant phase error, which is a phase error at the center frequency, which might be useful as a number to keep in mind with an example that I showed earlier when you deal with inversion and so on. As I said earlier, cross-correlation or cross-spectrals are the one often used in any computation for estimating the wavelets. Here is an example why it matters and why we have to QC the goodness of fit and accuracy. The cross-correlations are shown in red. We often apply a taper to those. The central part of the cross correlation is dominated by signal, and the lobes are usually dominated by noise. It's by choosing the length of that taper, shown in black, and the corresponding bandwidth, B, is that we control the wavelet length, and also we control the noise and signal ratio. If we choose the top length, that means we are harsh on rejecting the noise, and the estimated wavelet is slightly over smooth. The middle panel, we take the compromise into account. We keep the signal with the price of letting a little bit of the noise in, and that is probably just about right. The lower panel is when we are too generous and the noise is too much, and that is resulting to an under-smooth wavelet. This figure is summarizing what I've said so far. The horizontal axis is wavelet length. In the left side, that means short wavelet or not enough smoothing, which leads to bias or distortion of the wavelet. On the far right-hand side is where the wavelet length is too long, and therefore there is too much noise in the wavelet. And you see that the wavelet error is high. At the same time, goodness of fit is still good, though we don't want to be there because of the inaccuracy on the wavelet. A safe region is perhaps in the middle, which is not necessarily the minimum for wavelet error, but as I said, considering the compromise to have a good goodness of fit and also a low wavelet error. There are a number of other key factors, and we have to take all those things into account to make sure we have a good well tie. I cannot address each of those one by one in this presentation. What I can do is to focus on one, which is bandwidth. For the other aspects, I refer to the corresponding references. Here is a well tie panel for two wavelets. You can see that visually there is almost no difference in the well tie quality between the wavelet 1 and wavelet 2. Yet, if you look at the side lobes of those wavelets, one is on the right and one is on the left. That means those wavelets have almost 90-degree phase difference. And at the same time, they lead to the same well tie quality. So what's going on? If you look at the bandwidth of those wavelets, we see that the phase spectrum is just constrained by a narrow part of the bandwidth. In fact, you can fit many other phase lines to that bandwidth, which is what we saw earlier. If you choose a deeper section of the seismic, we have a better bandwidth, perhaps due to geology, less thin layers and so on. And that leads to a better constraint on the phase spectrum and gives us a much better well tie. This is summarized into these likelihood ellipses. When we have low bandwidth, the ellipses are basically too wide and too long, and that means the time and phase lag have large errors. With a good bandwidth, we have a better chance of constraining the lags, phase and time, and that means the error is low. Now I focus on broadband seismic data. What is missing? The reason we discuss broadband seismic here is because of a mismatch. The new technology on broadband seismic promises us to have low frequencies down to 2 Hz. On the other hand, well logs are in depth, and when they are projected in time, they are often very short, which means they cannot support the low frequency. So in one hand, we have broadband seismic, which has valuable low frequencies, and on the other hand, we have well logs, which are often short and inadequate to capture those frequencies correctly. Remember, that is both on the amplitude and phase spectrum. And we are also familiar with the figure now. We know that we have to take into account a compromise between goodness of fit and wavelet error. However, for broadband data, because of the low frequency, we have to choose a long wavelet length. That means we are forced to go towards the right of this figure, which is where the wavelet is most uncertain or the noise dominates. So what do we do about it? Firstly, the low frequency amplitude decay. Traditionally, we use populist type tapers. You see, due to the length of those tapers, instead of capturing that low frequency decay on the top right panel in black, we estimate the blue, which is biased, and it's not the low frequency decay we are after. In 2014, we proposed using multi-tapers. Multi-tapers have better resolution, higher resolution, and also protective against bias and noise. You can see the lower panel on the left and the corresponding multi-taper length in the frequency domain. That would lead to have a lower frequency decay on the right-hand side in blue, which is much closer to what we expect. Low frequency phase is another important aspect. It's very much likely that the low frequency phase is governed by the low frequency response of the recording system, that is geophone and hydrophone. And in the view of zero phase designature that we do in the processing, it's almost always necessary to choose a very long filter at that stage. And if that is avoided, it's likely that this low frequency phase is left in the data. Both hydrophone and geophone can be modeled with Butterworth order 1 or 2. On the top, you see a Butterworth order 1, which is 6 dB per octave. And on the bottom, you see a Butterworth order 2, 12 dB per octave. You see that in blue, the amplitude spectrum has a much sharper decay in the lower panel. It's also interesting to see that the phase also responds to the amplitude spectrum in a way. The top panel, the phase terminates at 90 degrees at 0 Hz, and in the lower panel, the phase terminates at 180 degrees at 0 Hz. So it's a good chance we can model this low frequency phase by using such approximation and put that in the well-tie estimate. Here I show 3 wavelets with identical amplitude spectrums. However, the phase at the low end are different, shown in black, red, or blue. If we use those wavelets to invert for a step function in the impedance domain, the correct wavelet, wavelet 1 in black, obviously gives us the ideal result, or as close as we could be to the ideal result. The 2 other wavelets with phase error in red and blue lead to those overshoots and undershoots around the impedance jump. That is obviously something we'd like to avoid. Generally, phase error leads to such artifacts in the impedance domain. So a possible solution we proposed in 2014 was to estimate the amplitude spectrum using the seismic data in a long window and many traces to reduce the noise, and also use multi-taper for a better handle on the low frequency decay. For the phase, we propose to use that Butterworth behavior, which is shown in the formula below. If the decay is 6 dB per octave, that means from the corner frequency, the phase terminates to 90 degrees at 0 Hz. And so on, you can increase the N, and so the phase behaves correspondingly. If we don't know the phase, really it's a trial and error. We have to estimate the impedance perhaps at the well location and fine-tune the phase spectrum so that we get the best match. Here is an example. The wavelet is shown on the top right. You can see there is no low frequency amplitude decay in the wavelet, and also the phase fluctuates as you can see as a function of frequency. The impedance at the chart level, where you see the green and red, see some artifacts. Those are exactly the same overshoots that we explained earlier. Also, the residual section is dominated by the low frequency. In this case, we changed the low frequency phase. It didn't help much. However, when we choose a constant phase wavelet, and also we estimated the low frequency decay on the amplitude spectrum, and so a long wavelet, you see those long smooth tails on the wavelet, led to have a good impedance profile, avoiding all those overshoots in the impedance section, and also you see the residual section is now minimized, and there is no low frequency left. This is all older stuff though. What is new? All I've explained so far led us to introduce 3 new techniques so that basically all the experience and the lessons we learned so far is incorporated on those techniques. Parametric constant phase, frequency domain least squares, and Bayes and time domain least squares. All the details and mathematics are explained in the paper shown above in geophysical prospecting. I explained briefly each of those one by one. Starting with parametric constant phase, the idea is that hopefully during processing they've done a good job on zero phasing the data, and what is left is perhaps a constant phase over the entire bandwidth. That would be a valid approximation and would help us constrain the least squares problem. With that, it's probably more useful for short log length. We calculate the amplitude spectrums using the formula which is shown below, and it's basically the convolution formula in the frequency domain. And for the phase spectrum, we use the cross-correlation and also the envelope of cross-correlation, and we compare the two peak points shown with little circles to compute the phase. If the data is zero phase, basically the cross-correlation and the envelope sit on top of each other. But you can clearly see here that the red curve doesn't represent a zero phase data. And in this case, there is a 60-degree phase lag. Frequency domain listed squares. It's a technique that we've used for a long time in the industry since the 80s, and it was also published by Walden and White in 1998. Traditionally, we use populist tapers to taper the auto and cross correlation, and then we do Fourier transform. That's because this is a technique in the frequency domain and we need the cross and auto spectra. What we propose is to use multi-tapering. That is a slightly different. That means we multi-taper on the data segments, then Fourier transform, and then we compute the auto and cross spectra. So we use the same algorithm, the same machinery, but we modify the cross and auto spectra estimation. Finally, Bayesian time domain listed squares. So parametric constant phase and frequency domain listed squares are very much frequency domain methods. Bayesian time domain listed squares, as it says, is a time domain method. However, it's often prone to noise. Originally, it was proposed by Gunning and Glinsky in 2006. You see the estimated wavelet on the left and what we desire to see in broadband seismic data on the right with those smooth and long tails. We may have some worst case scenarios where again the estimated wavelet is on the left and the desired wavelet is on the right. So we use the same machinery, but we try to improve the performance of that technique, especially when we have broadband seismic data. We propose to use two different priors for different purposes. Low order polynomial decay is a way that we modify the amplitude spectrum, but remember this is a time domain technique, so there is a little trick to do that in the time domain. And we did that by expanding using a Taylor expansion of the Fourier integral. The second prior is anti-overfitting tails. Remember, I said for broadband data, we need to have a long wavelet. That means in the wavelet tails, it's a very good chance that it's fitted by noise. We said in those tails, we'd like to have those samples correlated to each other so that they enforce correlation. That means some sort of a smoothing, which is anti-overfitting, and that rejects the noise. Let me show you some real data examples. This is an example, again, we discuss in details in the paper in Geophysical Prospecting from Northwest Shelf, Australia. Geology is gently dipping, and there are two wells available, and we discuss a rigorous QC approach, cross-validation, or you know it perhaps as blind QC. I show you some of the results here. So we do the extraction at well 1 and QC at well 2. That is what I meant by cross-validation. Here is the parametric constant phase wavelet. You see that wavelet, it's almost 400 millisecond length. You see the low frequency decay, and the estimated phase is 170 degrees. So that means probably there was 10-degree phase residual in the data. The phase error is around 6 degrees, which is excellent. That means it's a good candidate for inversion. The well-tie quality is also very good, as you can see on the synthetic and seismic in the left panel. The Bayesian, with those broadband constraints that I explained earlier, also lead to a similar wavelet. You see the phase spectrum of that wavelet is similar and also constant to what we saw earlier on the parametric constant phase. The amplitude spectrum has a good decay at the low end, and also the well-tie quality is very good, as you see on the left figure. Both wavelets behave very nicely and also consistently. Now the way we QC it is at the well 2. This well has not seen the computation on the wavelet estimation side. Yet we see an excellent match on the estimated impedance compared to the well log impedance in red and blue correspondingly. So you can see the absolute impedance, relative impedance, seismic, and also the model synthetic by inversion. What is useful to see is to look at the relative acoustic impedance in this case, or generally relative impedance estimates. And also, there is two attributes listed in the bottom, RMSE and cross-correlation. I often look at the RMSE to see for constant phase compared to Bayesian time domain wavelet. Constant phase is slightly lower, and also visually you can see a better match. So that means perhaps in this case, constant phase is a wavelet to choose. We did the same journey, basically computing wavelet at well 2 and QCing at well 1. We saw the same observation, so I skipped that for now. However, it's interesting to see whether that 10-degree phase that we estimated earlier with parametric constant phase matter or not. Here is acoustic impedance section along with the well trajectory as a QC, but using a zero phase wavelet, the same amplitude spectrum, compared with the constant phase wavelet with 10-degree phase. You see in those arrows that obviously if we ignore the 10-degree phase, some of those thin layers, which are very important, are clearly unseen by zero phase replacement. So it's very important to take into account the phase and also make sure that phase is correct by using the phase error. Here is a near stack amplitude around the target. Here is the far stack amplitude map around the target. Comparing to the near, you can see the AVO anomaly. And also with that, you can interpret the reservoir extension shown in white line. If we use the data and the corresponding wavelets, here reference wavelet using traditional method, we get the inverted facies, and in this case, a gas reservoir shown in red. Obviously, the estimated reservoir extension doesn't reach what we expect from the data shown with the interpreted lines or boundaries. If we use the exact same parameters and the exact same inversion engine, but we just change the input wavelets. In this case, we used broadband wavelets using parametric constant phase. Clearly see that the gas anomaly, the gas reservoir, now conforms to what we expect from the data and reaches to those thinner part of the reservoir as shown by the boundaries we interpreted earlier from the data. The message is clear. If we want to use broadband data effectively, we have to have broadband wavelets to represent the spectrum nicely and completely, especially at the low end of the spectrum. So I briefly discussed a quantitative approach to well tie and highlighted the importance of QC. I showed you how to QC the goodness of fit and at the same time as accuracy and deal with the compromise effectively. For broadband data, I briefly explained 3 different techniques. All have different mathematical backgrounds, but they complement each other. And we have to use all of those together to make sure the well tie is accurate. A good workflow is perhaps start with parametric constant phase and then use the other 2 methods to improve upon. I'd like to thank my colleagues for their valuable collaboration during the course of this work, and also various companies for letting me publish the result and sponsoring the Broadband Well Tie project. And finally, thank you for listening, and also please feel free to share this video or like it and get in touch if you have more questions.